Okay, so we left off with 7.5, part 1. We were talking about the different types of identities with sum and difference. We went through those for sine, cosine, and tangent. And then we looked at the double angle. So if you didn't get the tangent, sum, and difference, I'm just putting them on the board again. I think everybody had a chance to copy them down. So since we have a little bit of time, what I want to see is where this one comes from. Okay? Figure out like how does that even come up? So what did we say you can rewrite tangent as? If you didn't know this identity and you had to do a tangent problem, how could you do it instead? Yep?
Sine over cosine.
Hey, you could do it as sine over cosine. Okay, so let's take a look at that. Sine over cosine. So it would be, what would be your argument in each one of them?
Alpha plus beta.
Alpha plus beta. That's what you're taking the tangent of. And if I only had one of these problems to do, that's not an awful way to do it. It's going to take a little longer than just knowing the tangent formula. But we are going to look at what the tangent formula is. So, can somebody remind me, how do you do the sine of a sum? Are your trig functions grouped or are they mixed? Yep.
Sine alpha plus times cosine beta.
So sine alpha.
Cosine
And what goes between them?
minus plus.
Plus. Okay.
Oh, cosine alpha and then sine beta.
Yep. Cosine alpha, sine beta. You can double check it because each trig function should be applied to each variable. So the alpha gets plugged into the sine and the alpha gets plugged into the cosine. If alpha was getting plugged into sine on this side and this side, then something's wrong. Beta gets plugged into cosine, beta gets plugged into sine. Okay. Questions on the top? All right. Bob. Cosine of a sum. Can someone remind me, how does that one go? Yep.
Cosine of alpha times cosine of beta minus sine of alpha times sine of beta.
Yep. So that's where you keep your cosines on one side, you keep your sines on the other.
Would it be minus though?
Yeah, minus. Sine, alpha, beta. Okay. So there's first step. Any question on that? Now, if we look at that and compare it to what we kind of already know the answer is, there's something here that we can do to all of these terms, especially to make this one look like this one. I'm not going to worry about anything else right now. I'm just looking at that, and I already see something plus something in the top. That's kind of like this one. And I have a minus in the bottom, and I have a product of two things in the bottom. So a lot of this kind of looks similar to what it's supposed to be, except this part. This part that I circled is supposed to be what?
1.
A 1. So how could I make that part a 1? What could I do? Yep.
Divide the whole bottom by cosine theta cosine beta.
Cosine, what is that first one again?
Alpha.
Alpha.
Then cosine beta.
If you take and divide, and you have to do it everywhere, because if you have something like, let's say you had 3 plus 8 over 5 plus 2, and you wanted to make this a 1, you can, if you divide everything by 5. So you'd have something like this. That's perfectly fine to do. You just divided everything by 5. And that's what I'm trying to do here. I'm going to divide everything by cosine alpha, cosine beta, and it's going to force what's in the lower left to be a 1, which is what I want. And then hopefully it just forces everything else to be what it's supposed to be, automatic. Okay, so let's see what happens. All right, so we've got sine alpha, cosine beta, going to leave room because I'm going to write something in that I'm going to divide by, plus cosine alpha, sine beta. I'm going to leave some room because I'm going to put divided by something in a second. And then I've got cosine alpha, cosine beta. I'll leave some space right there. And then minus sine alpha, sine beta. So I basically copied over the problem again, and I just left some room to divide everything by something. And what are we going to divide everything by? Yeah?
Cosine alpha, cosine beta.
Cosine alpha, cosine beta. And we're going to hope we get a lot of things that just cancel out and reduce, and we'll see what happens. So divide everything by what's in that red box. As long as you divide everything by the same thing, you're okay. You can't do it just in certain places. You got to do it everywhere. Cosine alpha, cosine beta, cosine alpha. There's all kinds of things that are going to be canceling out here. Cosine alpha, cosine beta. Okay, let's start with this fraction in the upper left. Anybody see something that's going to happen there? Yeah?
Cosine beta, and cosine.
Those are gone. Okay, let's go to the one in the upper right. Anybody see anything that's going to cancel there? Yeah?
Cosine alpha.
Okay, that's gone. Let's check the lower left. Anything that's going to cancel there? Yeah?
All of it.
All of it. And how about the last one? Yeah?
When we simplify tangent.
We'll look at that in a second, but is there anything that cancels first? Okay, so we've canceled out everything we can. Now, let's focus on what's left. When you take the sine of alpha and divide by the cosine of alpha, what do you get? What's the sine divided by the cosine? Yep, that's the tangent. So we have tan alpha plus, what's the sine of beta divided by the cosine of beta? Yep. Tangent beta. Over, well, this whole thing turned into a 1 minus. And now, it's not quite lined up perfectly, but if you look at this, no, it is lined up perfectly. Think of that as two things. Sine alpha over cosine alpha. We just did that. What is that? Yep.
Tan of alpha.
That's your tangent of alpha. And then the other part of it is sine beta over cosine beta. What's that? Yeah, Nick?
Tangent beta.
Tangent beta. And I think that's the identity. So it really isn't that hard to derive it. It's basically one step. We divide everything. Once you set it up, you divide everything by this, and you automatically get it. And if we did the other one, which is the difference, it would be almost the same thing, except those two things that I just circled switch places. The minus goes to the top, the plus goes to the bottom, but then all the same canceling would happen again. All right, it's not too hard to figure out where that comes from. Any question on that? All right, so that's that. And well, I think the last thing we looked at was the double angle identities, but we didn't really do a lot with them. So we're going to practice a couple problems today. So this, I think, did we have time? Did we go through the proof of this? The sine 2 theta one? How did we rewrite sine 2 theta to figure that out? Yep.
Was it just sine theta plus theta?
Yeah, we did sine theta plus theta, and we applied a sine sum identity. All right. This one? So cosine 2 theta. let's try the same thing here. I've never tried that. Let's see if we get cosine squared minus sine squared. So cosine. Everybody agree that that's cosine 2 theta? Okay, let's write it out using the formula we know and see what happens. What's my formula for cosine of a sum? Yep.
It would be cosine theta times cosine theta minus sine theta times sine theta.
Yep, so it's cosine theta, and then sine theta times sine theta. Well, what's cosine theta times cosine theta?
Cosine squared.
That's cosine squared theta. And what about sine theta times sine theta?
Sine squared.
Sine squared theta. So it's actually a very easy identity to prove where it comes from. Cosine squared minus sine squared. Now there's 2 other versions of that, and they're all based off of a Pythagorean identity substitution. What's the Pythagorean identity that looks kind of like this, but it's a little different? John?
Is it the one where it's like, is it cosine squared plus sine squared is equal to 1?
Yep, sine squared plus cosine squared equals 1. And now, what if I wanted to get cosine squared by itself? What would that equal? Yep.
7 minus 1. Or 1 minus after.
What do I put here?
Sine squared.
Sine squared. Now, if you take this and put it right there, you'll get another version. Cosine squared is 1 minus sine squared minus sine squared. What would you get if you simplified that? Yep.
2 minus sine squared. Or minus 2 sine squared. Theta.
So you'd have 1 minus sine squared minus sine
Oh,
squared.
yeah.
It's like 1 minus x minus x.
1.
It's not this. Then those would cancel out.
Oh, is it
Like that.
Is it 1 minus 2 sine?
Yeah, 1 minus 2 sine squared. And you can derive the other version just by, instead of solving it for cosine squared, solving it for sine squared. Okay. So there's three different versions. The tangent one, I'm sure you could figure that one out by doing what we've done in the past. You could take sine 2 theta, you could take that formula, and divide by one of the versions here, and probably derive that identity just like the other ones. I'm not gonna derive that one. Any questions on that? All right, so let's take a look at this one. So this says to write 2 cosine x plus 2 sine x only using arguments of x. So you cannot have a 2 in the argument. Is there any part of what they gave me that's already okay, and I don't have to change it? Maybe?
The 2 cosine x.
Yeah, the 2 cosine x is okay because that doesn't have a number in the argument. It has a number in front, that's fine. So we're going to leave that. And how about sine 2x? How can I rewrite that so there is not a 2 in the argument? So
Sine x plus x.
So you could do sine x plus x, but then you've got to go back through and simplify that whole thing, which we've done, and we already know what it comes out to. Yep.
Is it 2 sine x?
Nope. 2 sine x. Tim?
2 sine x times cosine x.
Yeah, 2 sine x times cosine x. So that's the double angle identity, and we prove that. And so 2 sine x cosine x. And technically we've done what they wanted. We've rewritten everything with just an argument of x. Now, what if they did say to factor it? What could you factor out from here?
Cosine.
Even more.
2
2 cosine, right? You could factor that out of both. And why would you want to factor it? Well, because tomorrow we're going to be taking something like this and setting it equal to 0. And then we're going to solve it. So to solve it, you have to do one of two things. You either have to be able to factor it or use quadratic formula. Quadratic formula is going to be more complicated. If you can factor it, that's always easier. So we're not actually setting it equal to 0 today, so let's just practice factoring it. What would be left if I factor out 2 cosine x inside the parentheses?
Sine x. 1 plus sine x.
Sine x. Now that it's factored, if we had to set that equal to 0, that's 2 very simple expressions to solve. Set that equal to 0, you just have to divide each side by 2 and then do an inverse cosine. To set that equal to 0, you just minus the 1 and then do an inverse sign.
How could you pull out 2 cosine x out of there if there's no 2 cosine x on the right side as well?
There is 2 cosine x.
Okay.
Yep. Remember, multiplication, you can switch the
yeah.
order here. So you could pretend like the cosine x is right here if you want. Any questions on that one? All right. Let's try this one. Oh, and we're going to solve. So we'll see how far we take this, because this is getting a little bit into what we're going to try to do tomorrow. All right. Is there anything here that we don't have to change? No. When you're trying to solve an equation, you don't want numbers in the arguments. That's really going to mess it up. You have to get those numbers out. So when you have a 2 in the argument, not bad. You can deal with that. When you have a 3 in the argument, that just increased the complexity quite a bit. That's going to take a little bit longer to figure out. So let's start with the sine 2x. Can someone tell me how I can rewrite that so I don't have a 2? Yep, that's it.
2 sine x times cosine x.
Yeah, that's the easy one. Okay, 2 sine x cosine x. We took care of that. Now, do we know an identity for, that's a double angle identity that she used. Do we know a triple angle identity? There is one. We don't know it. I mean, there's a triple angle, there's a quadruple angle, there's as many as you want. But we don't know the triple angle one. So what we're going to have to do is break this down kind of one step at a time. What's another way of thinking of 3x? Then you can kind of break it apart, and then we'll handle each part separately with an identity we learned yesterday. Yep.
When we do x plus x plus x.
You could do x plus x plus x.
Or 2x plus x.
Let's do 2x plus x, because we have an identity that deals with a sum of 2 things. We don't have an identity that deals with a sum of 3. We could figure one out, but we don't have one. So we're going to break this down into cosine 2x plus x. Now this thing is going to start to really get big, okay, because of this part. What identity am I going to use on that? What's the name of it? Yep.
Is it the cosine sum?
Yep, it's the cosine sum. This part in front is just going to kind of hang out through every step until we get to a point where maybe we can do something with it. Okay, so now we got to do plus, and let's write the identity first. Cosine sum is cosine, cosine, sine, sine. And what goes between them?
A minus sign.
A minus. First, second, first, second. So 2x, x, 2x, x. Now, we don't have a 3x anymore, but to get rid of that 3, we really paid a price. We had to really make it a lot bigger than it was. And we have some other things that are okay. Cosine x is okay, sine x is okay. But these two things are not okay. So now, we have to focus on those. And the hope is that as we do this, eventually we start to get some things that cancel out. Once you've expanded it as much as you can, it should start to simplify. Now, this last one I'm not too worried about. I already know what that is, 2 sine cosine. It's this one that I'm starting to think about a little bit. Why do you think I'm thinking about cosine 2x a little bit more? Yeah?
Because there's multiple ways you can write it out.
Yeah, there's multiple ways to write it out, and I'm not sure what the best way is going to be. So let's just start with what we've got. 2 sine cosine. And I think what I'm going to do, I'm going to go back, is I'm going to use this one. You could use any of them, and eventually you can get to the same point, because these two are really just this one with a Pythagorean substitution. So let's try the 1 minus 2 sine squared, because I've done this before, and I know that that one will help us. So we're going to write 1 minus 2 sine squared, and you have to be careful, because now that's a distributive property. That 1 minus 2, whatever you change cosine 2x to, it's being multiplied by cosine x. I changed it to something with 2 terms. They're each multiplied by cosine x. All right, and someone remind me again, what's sine 2x? Yep.
2 sine x times cosine x.
2 sine x cosine x times sine x again. Okay, so at this point, this is what I call, this is kind of like almost like the peak here. We've probably reached as complicated as it's going to get. Now, the hope is that we can try to start simplifying. All right, let's see. Does anybody see something? It's kind of a pain to really rewrite it just to do this, but does anyone see something we could do at the end? Yeah?
Would the 2 sine x cosine x and then negative 2 sine x cosine x cancel out?
If this sine x wasn't here, if it was like that, then yes, you'd have a positive 2 sine cosine and a negative 2 sine cosine, and you could just cross them out. But this isn't really a sine, because it's multiplied by another sine. So what's really this last term going to become?
2 sine squared x.
2 sine squared x, and what else?
Cosine.
Cosine x. So I am going to rewrite it just to multiply these two together. Or you could just erase this and you could just put the 2 on. I'm afraid if I do that and look back at your notes, you'll be like, wait, where did this sine squared come from? So I'll just rewrite the whole thing. If I was actually doing this, I would not be rewriting it like this. I also want to look, before I keep going, am I going to end up distributing that cosine? I think I am. So if I'm going to distribute that cosine, it probably makes sense to do it in this step, so I don't have to rewrite it again just to do that. Again, I'm just kind of thinking as I go. And then I think we might see something that could cancel, or let's see. So we've got cosine x minus 2 sine squared cosine minus 2 sine squared cosine. Okay, that's good. I see something here that we're going to be able to work with in a second. Okay. Let me double check I didn't copy anything wrong, because that's the danger of writing it over and over. You copy something wrong. 2 sine cosine plus cosine minus 2 sine squared cosine minus 2 sine squared cosine. Okay. Anybody see something I can do?
I've got a question.
Yeah.
How'd you get to minus 2 sine squared x cosine x?
Which one? There's multiple ones.
Yeah, how'd you get both of them? Like, how'd you get 2 of them?
Well, when I distributed cosine to that, I got minus 2 sine squared cosine.
Yeah.
And then minus 2
Oh.
sine squared cosine.
Oh, okay.
So how many sine squared cosines do I have?
4.
How many?
2. 4. 4.
Well, how many really? Not 4.
0. I don't know. 1.
Negative 4.
Negative 4. Well, we're going to put minus 4. Okay? So let's combine those two together. So copy this again. Just put the cosine like that. And now we've got minus 4 sine squared cosine. So that did make it a little smaller. Okay, now, when we look at that, does anybody see, I'm just going to give you kind of a hint. This is a term, this is a term, that's a term. Does anybody see something that's in common to all of those terms?
Cosine.
Cosine x. So what can we do with it if it's common to all of them? Factor it out. And then I want you to see what you're left with. So let's take the cosine x, factor it out. What would be left in the first term?
2 sine x.
And I'm going to put that here. So what I'm doing is I'm factoring it out and I'm trying to write it in a certain order at the same time, so I don't have to copy it all over another time. So that, give me that. What if you factor cosine x out of the middle term?
1.
So you'd be left with a plus 1. And what if you factor cosine x out of the last term?
4. Negative 4 sine x.
Negative 4 sine squared x. I just forgot my x here. Okay. And it said solve for zeros. What does that look like?
Quadratic.
That's a quadratic, basically that is a quadratic formula problem. Whenever you get something that's of the form a variable squared plus or minus the variable plus 1, that is a quadratic formula type equation. So in general, something like this. Something squared, it could be plus or minus something, and then the last thing has to be a constant. You can put anything you want in those boxes, and it will be a quadratic formula. The traditional thing you put in is a variable, like x squared plus x plus 6. And if you had a problem like let's just take that one for example. What are you solving for in that equation?
Where it crosses.
Well, yes, graphically you're solving for where it crosses the x-axis, but in general you're trying to find the value of what?
X.
And even more general, you're trying to find the value of this. When you solve a quadratic equation, you're always trying to solve for whatever is right in the middle, or the square root of the first term. That's what you're solving for. You're not solving for x squared, you're not solving for 6, you're solving for what's in the middle. Let's go back to this. This equation in the parentheses is pretty much like this. If you can solve this, then you can solve that. Here, you're solving for x. What are you solving for here? Sine x. You're solving for sine x. So when you do your quadratic formula, it's not x equals negative b plus or minus all that stuff. It's sine x equals negative b plus or minus all that stuff. All right. So let's see if we can solve that by first identifying A, B, and C, just like you would in a regular quadratic. What's A here?
-4
Negative.
sine
So A is just a constant.
-4.
Yep. And B?
2,
C.
1.
Now do the quadratic formula with -4, 2, and 1. But don't say equals x. Say equals sine x. So we got negative b plus or minus square root of b squared 4ac all over 2a. Double check, make sure I did that right. And that equals sine x. Okay, what do I get under the square root when I do 4 plus 16? 20, right? So minus a minus cancels out. 4 times 4 is 16, plus 4 is 20. Now, if I was worried about leaving a final answer, I'd probably want to reduce square root of 20 to 2 root 5. But that's not a final answer. That's going to be plugged into something. So I'm not worried about fixing the square root of 20. Not even really worried about reducing the 2 and the 8. I mean, you could, if you broke down this root, you could. But let's just leave it like that. Questions on just getting to that step? Okay. So now, how do I get x? Because I don't want to know what sine x is. I want to know what x is. So get rid of sine. What do we have to do on both sides? Yep.
You take the inverse sine.
Yep. To take the inverse sine. So x equals the inverse sine of negative 2 plus or minus square root of 20 over negative 8. Let's see what those come out to. Now remember, when you do inverse sine, it has a domain of -1 to 1. So if I get an error, it's probably because one of these values, either the plus or the minus, is outside -1 to 1. And if it is, then I just ignore it. But if it's not, I'm going to write it down.
Can we simplify this? Can't we change square root 20 to 2 square root 5 and then
Yes.
simplify it so it's -1 plus or minus 2 plus or minus square root 5 over -4.
So you can simplify it, but because all I'm doing with it is plugging it into inverse sine, and that's going to be my final answer, that's just really an extra step where we could make a mistake. So you could, but I wouldn't. Is there any questions why I wouldn't do that right here? Okay, so let's just plug it all in the way it is, and that might even be less to plug in if we reduced it. I don't know, I'd have to see what happens. So -2 plus the square root of 20. Oops. And we need to be careful with parentheses. We want to divide that by -8 inside the inverse sign. So I'm going to have to fix this. Divided by -8, but I need an extra parenthesis around the numerator. So that is how you type it in. So -2 plus the square root of 20, do that first, then divide by -8, and then once you get that, take the inverse sign. Okay, so I got -18. That's degrees. Now, let's type the same thing in again, except we're going to make this a minus. And I got 54 degrees. All right. So I think we found our solutions here. So we set this equal to 0. The last thing we have to do is set that factor equal to 0. But luckily, that's just a single factor. We should be able to just figure that one out in our head. So no need to do quadratic formula with cosine x. Just how do you get rid of cosine on each side? Inverse what? Cosine? So x is the inverse cosine of 0. So what I do for that one, I think of cosine in my head. It looks like this. And you're trying to figure out where the graph of cosine crosses the x-axis. It crosses at the first quarter and the third quarter. Does anybody remember what those 2 points are in degrees, since we did the other 2 in degrees? Yep.
It would be pi over 4 and then pi over 4.
Well,
Degrees.
not-
Yeah.
we want degrees, but those wouldn't be the ones in degrees.
What is it? 45 and
No, what's the first quarter of the cycle? 90. And the 3/4 mark?
270.
270. So, if we did everything right, we should see it cross at those points. I'm going to have to look at the negative part of the x-axis a little bit. If I wanted, what can I add to negative 18 to make it positive? 360, right? We could add 360. Let's just keep it as a negative, and let's just look at it that way. Not normally how we do it, but so let's graph sine 2x plus cosine 3x. Let's see. I'm going to do degrees. That's fine. I'm going to set my window from, I don't know, I'm going to go like negative 50 because I want to see that negative 18. And I'll go up to 360. Let's hit graph. And notice even the speed it's graphing it at, it's taking a while because it's a complicated trig function. And if we get a couple more answers than we got, I know why, but we're going to get into that tomorrow. So let's calculate this 0. At least if we get the ones that we got, we know we did it right. If we don't, then something's wrong. Okay, so I'm just going to check. I'm hoping that's close to the negative 18. Yep. So let's put these down here. All right, so there's one of them. That's the negative 18. Let's check second calc 0. Hopefully this one is around the 54. That's what we're hoping for. Good. So there's another one. So we got a 0 at negative 18. We got the 54. I think you can tell it crosses at 90 because it goes right through the tick mark. So I can verify it, but it's 90. Okay, so there's another answer at 90. And let's check for 270, but again, I think you can see it by just looking at it. So 270, there is one right here. We didn't talk about that one. That's fine for now. And there's your 270. So those are all the ones we found. The 270, the 90, the 54, and the negative 18. Now, with these two, that's pretty much all you can get out of them. It's these two that are giving us the other two answers that you're not seeing, that we didn't get. This is a diagram where we can figure out where certain trig functions are positive and where they're negative. And I am guessing that if we did 180, I think, minus 54, I'm guessing that there's an answer at 126. We basically got it from this 54. I just haven't shown you how or why did I just subtract it from 180. But let's check 126. Yeah, it's going to be 126. And notice, to get that 126, I didn't really have to do that much more work. I just had to take one of the answers I got and subtract it from 180. So I didn't really have to do much more. The more that I did, I'm going to explain that tomorrow. And there is one more answer we didn't write down, and we could get that one from this negative 18. But we'll do that tomorrow. Okay, so that problem had a lot in it. So when you have a 3 inside that argument, it really makes it a mess. And if you had something like a 5 or higher, forget about it. It's going to be really, really, really bad. Okay, so 3 is the highest you would ever see. But does anybody have any questions on that? And if you understand that idea of how we use the quadratic formula here, that's a lot of what tomorrow is going to be as well. So the last thing, I'm going to give you these formulas. We don't really spend a lot of time doing examples with them. I'm giving them to you purely because if you do take calculus next year, it's nice to have all your identities in one place. Especially Mr. Babb said they're not all in the calculus book. So if you keep your pre-calculus notebook, you could flip back to this section and you have every identity that you'd pretty much need. So we talked about how to deal with angles inside of the argument that have a times 2. This is how you deal with angles inside the argument that have a divide by 2.
There's a lot of identities, huh?
What's that?
There's a lot of identities, huh?
Oh yeah, there's thousands of them. I would say the ones that I've given you up to this point, we've done all the ones that we're going to do. The common ones are the Pythagorean, reciprocal, quotient, double angle, half angle, and sum and difference. So I think I taught you guys about maybe 20 of them. But yeah, literally, there's thousands. Yeah. You could come up with third angle identities, quarter angle identities. I mean, you can just keep coming up with these things all day. And what the half angle identity is, it gives you another way to figure out a problem like this. You guys should know how to do that using a difference. You could do it as 45 minus 30. But if you forgot that identity, can anybody think of a number that's a multiple of 30 or 45, that when you divide it by 2, you get 15? Yep, 30. You could figure out the cosine of 15 that way. And maybe that's simpler than doing cosine 45 minus 30. It's up to you. But it does give you some more ways to figure out different things. And we don't go through the proofs of these identities. Okay, any questions on that? All right, so I think the big thing for today was just to kind of, if you understand the quadratic formula, that's the most important thing to take out of what we did today. So those are the questions for tonight. 18 only has an argument of 2's in it, so that won't be too bad. 29, that's a graphing calculator question. Let's see, 31, that's fine. 37, that's another graphing calculator. 41, graphing calculator. And 45. So I don't think that'll take you too long.